Hello everyone, this is Professor Iris Miano. I've got a Day 17 lecture for you for Math 2 Pre-Calculus. Just one section we'll be covering. It is quite dense though, and it is section 5.3 concerning properties of trigonometric functions. So let's start by recalling what the positional trigonometric functions are, x being cosine theta, y being sine theta, and then their corresponding quotient and reciprocal functions as well. So you may recall that on the unit circle, the outer edge of the circle has ordered pairs xy that can be associated with angle measuring in either degrees or radians called theta, and that determines the amount of swing is the terminal side's location, the terminal ray of the angle, and the ray intersecting a unit circle has a position xy, which is the cosine and sine of the angle theta respectively. Okay, and then there are four other trigonometric functions that can result from that by either taking the quotient of the cosine and the sine, or vice versa, or the reciprocal of the sine and the cosine. Okay, so let's get a little bit deeper into this with the properties that we're going to be learning here. But before we get too far into specific properties, it behooves us to talk about domains and ranges. So you'll notice that I have a fun GIF right here, which shows the sinusoidal waves for the sine function and the cosine function, and how it relates to unit circle. So notice the unit circle spinning around in green, and its positional point is corresponding to the x value, which is in blue, and its corresponding position is being tracked in terms of theta in the form of a cosine wave. Similarly, the y value of the spinning positional green dot is being tracked in the red trajectory, and that gives us the sine wave of theta. So theta can actually have any value possible. So for both the sine and the cosine functions, the domain for both of those is any real numbers. But as you can see, the x and the y positions here range from -1 all the way up to 1. See here it goes down to -1 and then 0 and then back up to 1 again, and loops back down again for both cosine and sine. So if you really like this GIF and you want to look at it some more outside of this lecture video, you can press the hyperlink in the PDF file of these lecture notes. All right. So, and then there's some other things that we can talk about as far as domain and range are concerned for the other four trigonometric functions. So, of course, with tangent and secant, because we for both of those instances we have cosine in the denominator space, so anytime it takes on a value of 0, i.e. pi over 2 or 90 degrees if you're into the degrees thing there, then we're going to have to remove those two items from the domain. Similarly, for cosecant and cotangent, the sine function is going to be in the denominator space for those functions. So anytime the sine is equal to 0, which is going to be at pi or 180 degrees, we've got to take that out of the domain. So there are some domain restrictions for the quotient functions and the reciprocal functions. And furthermore, when you're talking tangent or cotangent, there are no restrictions to the range. They go off in both directions for all real numbers, and but there is a little bit of a restriction going on for cosecant and secant. Okay, great. And again, like we saw earlier here, sine and cosine, the range values, the outputs for x and y in the unit circle range from -1 to 1, as we can see here in the GIF. Okay, great. So table 4 in the textbook puts all of this information together for easy reference. Okay, great. So we have already touched on briefly about the periodic nature of our trigonometric functions, which is to say that you can spin around unit circle as many times as you want. And when you spin more than one full revolution, it can be thought of as equivalent to just the positional location starting from the initial ray position to the terminal ray position. So for instance, like you see here in figure 36, this is a specific example. In the green trajectory that I'm tracing over with my mouse here, goes one full revolution of 2 pi in a rotation plus an additional pi over 3, right? Which is the same as saying, 7 pi over 3, I think is the way you can define this initially. So if you had sine of 7 pi over 3, that would be the same as 6 pi over 3 plus the 7th pi over 3, right? You can separate that out and say that the 2 pi is equivalent to absolutely 0, radians in measure, and then just say, okay, it's the same as ending up just traveling the pi over 3 distance, okay? So again, the green trajectory is moving 7 pi over 3 in rotational distance as far as the radians are concerned, but that's equivalent to just moving from the starting position just to the pi over 3 position. You'll end up in the same place no matter what, and so that's what makes them equivalent. In fact, for any time you're encountering sine and cosine functions such that you can separate the theta measurement by multiples of 2 pi, if you could separate those out, essentially those just zero out, and it's equivalent to whatever the leftover theta is here. That's what figure 37 is trying to convey here, and also this very first theorem right here, or relationship, is trying to allude to the definition of being periodic in general. So this just shows you how sine and cosine are both periodic, and furthermore that their period is 2 pi for both instances, which is just to say that as you move around unit circle, hold on, almost there we go, I did sneeze. Whew. Excuse me there. So it's just to say that a rotational measurement of 2 pi is one complete revolution around unit circle, and so it's essentially considered, as far as finding the output for the sine function, equivalent to not moving at all, okay? So hopefully that makes sense. In general, a function is called periodic. I'm here at the definition of periodic in this yellow box. If there's a positive number p such that you add it to your theta, and it's like you just ended up back at your theta again. This p value just basically took you one or maybe even multiple full rotations around your particular periodic function. Okay, so now all 6 trigonometric functions are periodic, but they don't all have the same period. So notice that sine, cosine, cosecant, and secant all have the same period of 2 pi, okay? While tangent and cotangent have a period of just pi. So we'll talk about that more specifically a little later when we get into graphing these things. It'll be a lot more evident what we mean by periods of 2 pi versus period of pi, okay? For now, we just want to practice using the fact that we know that these trigonometric functions are periodic and that we know what their period is. We want to practice using that fact in order to find the exact values of, let's go for these three examples here. Starting with the cosine of 420 degrees. Yes, and we'll be going back and forth between degrees and radians for our angle measure. We're going to have examples of both for every type of example here, okay? So our job is to find however many, because we're working in degrees, how many degrees, this is the question you want to ask yourself, how many degrees does it take to go a full revolution in unit circle? How many degrees does it take for one full spin? Well, that'll be 360 degrees. Okay, let's get purple going here. So can we separate out 360 degrees? Sure we can. And then what is left over? Well, 420 degrees minus 360 degrees is going to give us what? That'll be 60 degrees, right? So you can separate these values here. And this is one full revolution, right? So essentially, this bit just kind of zeroes out. So it's the same as saying, what is the cosine of 60 degrees? Okay, and for this, if we want to, we can reference unit circle. So on a different PDF, or sorry, a Word document, I have unit circle that I can reference from time to time if I need to, until of course I memorize it. So here is 60 degrees, and we were asking what the cosine is. So that's going to be the x value in the positional, information, the ordered pair information. So that'll be a 1/2. Okay, let's go back to the lecture notes. So this will be equal to 1/2. Final answer. Right. Next example, we have the sine of 9 pi over 4. 4 being in the denominator, I would love it if I could separate out like maybe an 8 pi over 4, because I know that that reduces to 2 pi, and that's in radians, distance measurement for the angle that's a full revolution. So that's what I'm going to strive for. So go ahead and inside of your sine, take out an 8 pi over 4, and then add to it the leftover. Well, there's 1 pi over 4 left over in that instance. Here, again, this goes to 2 pi, which is equivalent to 0, right? Oh, sorry, this goes to 0 degrees. It's equivalent to that. All right, so then we're just left with pi over 4. So, therefore, this is equal to the sine of pi over 4. And what's the sine of pi over 4? Okay, look at that unit circle again. Where's pi over 4? Here it is. Okay, it's right in the middle of the swing associated with the first quadrant, aka 45 degrees, but we don't care about that. What we care about is finding the sine, which awesomely for this one you can't go wrong because both the cosine and the sine have the same value. So cute. But really we're going for the y value on this ordered pair, technically, if we want to be super accurate with what we grab, and that'll be the square root of 2 over 2. Okay, so going back here, this will be square root of 2 over 2. Okay. Great. Last one, let's go cotangent of 17 pi over 4. Now this one will be a little bit more tricky because the cotangent, first of all, we want to recognize that its period is pi, not 2 pi. So we want to be looking to see how many whole pies we can be separating out here. So denominator of 4 down there, it looks like I would want to have something a multiple 4, the largest multiple of 4 in the numerator for the number of pies that I want to separate out. So, and then we'll deal with the fact that it's a cotangent. It's one of those quotient functions. We'll get to that in a little bit. But for now, I just want to deal with the period business. So the largest multiple of 4 that I could see being separated out from that 17 would be 16 pi over 4. So if I have 16 pi over 4s, and I add another pi over 4 to it. Cool. Then what does this simplify down to? Well, that simplifies down to a grand total of 4 pies, which is like how many periodic revolutions? Well, again, cotangent is has a period of pi, so this is like 4 individual rotations according to its own particular period. So that means that that is also equivalent to 0 radians, okay? Cool, so hopefully that makes sense to us. Now, what's cool about this is 4 pi also would have worked for a different trigonometric function of involving sine or cosine, or its reciprocal functions, but that's neither here nor there. No, we just want to find multiples of pi to be able to separate out and then focus on what's left over, because that's where it's going to be equivalent. So that'll be equal to the cotangent of pi over 4. And what is the cotangent? Do we remember? The cotangent is like x over y, and x is cosine and y is sine, right? So we could say that this is equivalent to cosine of pi over 4 over sine pi over 4. And do you guys remember what pi over 4 had for its cosine and its sine? The same value, okay? Right, we can reference unit circle. Pi over 4, again, is at 45 degrees. And cosine and sine are both pi over 2. So that means that the quotient here will be pi over 2 over pi over 2, which is, I mean, we could just go straight to saying that the final answer here is 1, if we are so comfortable. If we need a little bit more discussion on that in class, you just let me know, okay? So that's how I would deal with those first three examples, where again, we are using the fact that these trigonometric functions are periodic in order to simplify these things. You need to, provided that you are given degree measurements that are not just like straight up on your unit circle, which is the case here. We go a little bit beyond a full rotation, or in some cases quite a bit, like several more rotations out. I'm talking about number 24, according to its period. You note what the particular period is for that type of trigonometric function, and you use that to find the equivalent of full rotations, and you focus on what's left over, and then you find the cotangent, sine, cosine of that, whatever your trig function happens to be. Okay, moving on. Great. So if you know either the sign of the sign of either positive or negative of two trigonometric functions at a given theta, one of them has to involve the sine function and the other has to involve the cosine function, or be the sine and the cosine function, then you can determine what quadrant your theta lies. And this is very important information, particularly for some of the applications that you have coming up. So here in the form of table 5 and figure 40, we have some just what's the word I'm looking for? Some reference information. So if you are know what quadrant your point is in, then you know what sign your and by sign I mean SIGN, what SIGN your SINE function has, or cosecant, and then also cosine, secant, tangent, cotangent. They all have their own little categories here, okay? Of course, the sine is related to the cosecant because the cosecant is the reciprocal function to the sine, so they're going to have all of the same sine characteristics going on in regard to what quadrant they live in. The same is true for cosine and secant because the secant function, remember, is the reciprocal of the cosine, and the same is true in relationship with the tangent and cotangent. Okay, and so here is just a table of this information. Here is a little bit more of a visual representation with the sine, cosecant, tangent, cotangent, cosine, and secant, and when they're all positive. Okay, so there you have it. Okay, so let's take this information and implement a few examples. Let's go through a few trials of being able to determine what quadrant theta has to lie in, given just two pieces of information. You have to be given some information about a cosine function, or something that's involved with a cosine, or and the other piece of information has to at least involve a sine function. And for number 30 here, we have a cosine signage explicitly given. The cosine of theta is positive or greater than 0, right? That's what this says. And then the tangent theta being a positive as well tells us, believe it or not, something about the sine, or at least that's what we have to glean in order to determine what quadrant the the theta has to live in. So obviously for this one, we know that cosine being positive means that the x, right, is positive. So x being positive, it's either in quadrants, what, 1 or 4. And so from here, we need to determine, since tangent theta is equal to, if you recall, y over x, or the sine theta over cosine theta. And since we know that the cosine theta is positive, the only way the tangent is going to also be positive is if the sine theta is positive as well. So this implies that sine theta also must be positive. So sine theta is the y, right? So the y is positive, the x is positive. What quadrant are we in, folks? We are in quadrant 1. So therefore, here's my triple dot symbol. That means it's mathematical shorthand for the phrase therefore. Theta lives in quadrant 1. And we use Roman numerals for this biz. Okay, cool. Let's do this again, but a different scenario. Here, the cosecant is positive, okay? So what does that mean? That means that 1 over the sine is positive. 1 over sine theta is positive. So therefore, sine theta has to be positive. And therefore y is positive. So here's like the line of reasoning that you can get to in order to conclude that the y has to be positive. So that means what? You're either in quadrants 1 or 2. And now the other piece of information here, cosine being negative, means that the x value is negative, right? Because cosine theta equals x. Okay, so positive sine, negative cosine, so the positive y, negative x, that means you must be in which quadrant? Quadrant 2. Yep, that's the only one that matches this scenario here. So theta lives in quadrant 2. So I just knew this stuff, right? But if you're like, ooh, you know what, I'm a little bit rusty on what the signs of x and y are in terms of quadrants, well, that's exactly what this reference information is here, right? X and y are both positive in quadrant 1. X is negative, but y is positive in quadrant 2. Quadrant 3, they're both at negative, x and y. And quadrant 4, x's are positive, but y's are negative. Okay, so yeah, feel free to reference this figure 40 stuff if that information is a little rusty. Okay, great. Moving on. So here's where the reciprocal and quotient identities are formally defined, but we've been already taking this information for granted, at least the way that I've been thinking about these trigonometric functions. So now is the time when we're just like, oh yeah, let's go ahead and just make it formally, abundantly known that the cosecant is equal to 1 over the sine, the secant is equal to 1 over cosine, the cotangent is equal to 1 over tangent theta, or you could call the cotangent the cosine theta over sine theta, right? As is shown here with the quotient identity, okay? So yeah, the reciprocal identity, that's also a quotient identity, that's the cotangent, okay? And yes, also the tangent is the sine theta over cosine theta equivalently. Okay, so let's see, what else is next? Some more examples. So we're going to use these facts to find the remaining 4 trigonometric functions in a couple of different scenarios here, knowing the sine and the cosine. So how shall we go about this? Well, what we do generally is, yeah, it's just basically plug and chug. So the sine and the cosine are here. So what I like to do next is the tangent theta, which is the sine theta over cosine theta, right? Or you could just go straight to putting these values in ratio with one another. So that's 4/5 in what I like to call the supernumerator, when you have complex fraction. There's like the main division bar, which is here. The numerator is a fraction, and the denominator is also a fraction. So when you have this, believe it or not, when the denominators of each element above and below the main division bar are the same, you could just kind of cross them out. That's a little bit of algebra trick there for you. And then there's one negative sign in the entire problem, so it could just kind of be pulled out in front. And therefore, you can go straight to the final answer, simplified all the way down, of -4/3. That is going to be your tangent value. Now, underneath the sign, I would recommend that you do the cosecant, because it's the reciprocal function of the sign. So you're just going to flip this over. The cosecant of theta is 5/4. How do I know that right off the bat? Well, the cosecant is the reciprocal function to the sine, and so therefore the value of the cosecant at theta is going to be the reciprocal of the value of the sine at theta. So just flip it on over. And then the secant is the reciprocal of the cosine. So just flip this one over, keeping its negation, all right? So, or that effect that it's negative. So therefore, secant theta will be -5/3. And then lastly, the cotangent, well, that'll be the reciprocal of the tangent. So cotangent theta, therefore, will be -3/4. We'll go ahead and box those up for you. Boop, boop, boop. And there you have it. Okay. Cool. Let's do that one more time with a different example here, though. Ooh. Harder to work with numbers, but nothing we can't handle. Again, I recommend that you start with the tangent of theta, because that'll be the reciprocal of what you are initially given. So go to √2/3 in the supernumerator over the main division bar, and -1/3 in the super denominator. Okay, again, just like we had for the previous one, notice that your denominators are the same, so they can just kind of cancel out. The denominator therefore becomes a 1, so this will just be like, you know, all living in the numerator, and then yes, it will be negative, so pull that out in front. So therefore, the tangent theta in this scenario is -2√2. Yep. And so then do the cosecant next. Cosecant theta is going to be the reciprocal of this bit right here. So there's a little bit of work to be done, nothing we can't handle though. 1/2√2/3. So therefore, since you have a fraction in your underneath the main division bar, it's the same as taking the reciprocal of it, right? I mean, or we could have thought about it that way from the get-go. In fact, let's go ahead and do that. Sorry, let's think about this a little bit differently, at least in the first step. Let's just take the reciprocal of this right off the bat. And then we recognize that we need to rationalize the denominator. So multiply it by a fun 1/√2/√2. Okay, these √2's will multiply to give you a factor of 2 down below. Multiply that with that factor of 2 that's already there. And therefore your cosecant of theta becomes 3√2/4. Okay. Now, the secant, I'll go ahead and kind of direct you over here from the cosine because it's the reciprocal of the cosine. The secant of theta will be, oh, that's easy enough to do. Just flip this -1/3 over to get a -3. That was easy. Now, lastly, we'll do the cotangent of theta, which is the reciprocal of the tangent, is the way I like to think about it most often. Now we've got to rationalize the denominator here. No sweat, just multiply it by a fun 1/√2/√2. These √2's multiply together give you a factor of 2. There's still a 2 down below, right? This is going to move up to the front, basically. And so that'll be a denominator of 4√2 in the numerator. So all in all, cotangent theta will be -√2/4. If I'm not mistaken, checks notes. Yep, that does That does check out. So these are all of your 4 trigonometric function values. Okay, great. So next, what shall we do? So now we want to introduce some more identities that are associated with basically this unit circle equation here. X squared plus y squared equals r squared, but since it's unit circle, your r is a 1. So instead of putting r squared here, we put 1 squared, but the value of 1 squared is just a 1. Okay, so then from there, what can we do? We can do a series of manipulations, okay? And then we're going to get to a very super duper duper intensely famous trigonometric identity. This trigonometric identity is going to follow you into many higher levels of mathematics. It's going to go through all the steps of your calculus series. Like, you're going to see it forever and ever. And this is day 1 as far as your pre-calculus class is concerned. Okay, so the thing that is done, so everything that I'm going to do are things that can be done. Like, obviously I'm not going to be breaking any rules that have already been established. You may wonder why we're doing some of these performing some of these steps, but it's just to get the form of this a very super famous trig identity that you're going to use oh so much. So in any event, for aesthetic purposes, we're going to switch the position of the x squared and y squared terms. We're going to redefine them in terms of their sine and cosine theta counterparts. Okay, so do a direct replacement of y as a sine theta, and then same thing for x cosine theta, and they become squared. And then we need to define another thing here, which is to say that when you square a sine or you square a cosine function, it's the same as squaring directly onto the function itself. Notationally, it just has a little bit of a different flair to it, where you put the exponent directly on the sine and the cosine function before the theta and no parentheses. So this is just standard notation. So I just wanted to explain how you get from one to the other, and how the sine squared theta is defined exactly as taking the value of the sine theta and squaring it, which is indicative in which you see in this step right here. Okay, great. So here we go. Here is our very first trig identity that has any squared terms in it, basically. This one's, like I said, super famous. You're going to use it a lot. And then you may notice further down on this page, there's a couple other ones that look kind of familiar but have different trig functions in them. How do you get these other ones? Well, it turns out if you take this equation 5, sine squared theta plus cosine squared theta, and if you divide both sides by cosine squared, so divide both sides by cosine squared theta, you'll get this one. And if you, from here, from the original one, divide both sides by sine squared theta, you'll get this last identity. Sine squared theta. Oh, sorry. Get this one. So, but you take this and you do this to it, or you do that to it. Then you'll get these other identities. Okay, so, take my word for it or try it out yourself, and you'll find that they, these other two trig identities presented in equations 6 and 7 do arise in this way. So they're equivalent to this first one that I'm boxing up in hot pink, okay? That is a super powerful piece of information that's going to allow you to write proofs, solve trigonometric equations in your future. It's going to have a lot of application for you, okay? Now, for the time being, let's just all recognize that the book was so nice in putting together all of the fundamental identities into one yellow box for reference. There it is, so cute. So let's go ahead and use this information, and if possible, like really in the next couple of examples, we're really going to use this trig identity, I think. Well, no, that one is going to be appropriate for this one right here. Oh, and then we'll use a different trig identity here for number 54. Okay, so let's go ahead and we'll reference these identities here as it becomes useful for us. And let's go ahead and find, what does it say for the instructions? Find the exact value of each of the remaining trigonometric functions of theta. And what are you given? You're given one value. Cosine theta is 3/5. And we know that theta is in quadrant 4. So if theta is in quadrant 4, then we know that, and obviously the cosine theta is positive, and sure, the x value is positive in quadrant 4. What do we know about the y values in quadrant 4, aka the sine theta? Well, this will tell you that sine theta has to be negative, less than 0, okay? Let me make that a little bit more nicer to look at. That's a little bit better. Okay, so we'll keep that in mind. And let's also use this identity right here in order to solve for sine theta, okay? Because we know the cosine, and then otherwise there's just a 1, a constant term, and then there's a sine squared theta in there, but we can unpack it to such a degree that we can solve for the sine theta trig function, okay? So let's go ahead and just put sine squared theta plus cosine squared theta, which is the cosine of theta, which is 3/5 quantity squared, equal to 1. Okay? Great. Let's go ahead and square this fraction right here, and we'll get sine squared theta plus, let's square the 3 and square the 5. We get 9/25. And that's equal to 1, which we can redefine as 25/25. Why would we want to do that? Well, in the next step, we're going to have to subtract 9/25 from both sides. And I'd rather do it from 25/25 rather than this whole number of 1, wouldn't you? Yup. So that'll get eliminated here. And then we'll be left with sine squared theta equals 16/25. Cute. You guys see how this is nice? We're going to take the square root of both sides and just the principal square root, right? Or wait, no, sorry, not at all. Our sine theta needs to be negative, doesn't it? Okay, so we're actually going to, technically, algebraically, we need to have both the plus or the minus square root, okay, which will be sine theta equals plus or minus 4/5. You guys see that? Because 16 square rooted is 4, 25 square rooted is 5. And then we have the plus or minus option. But wait, it was stated earlier that the sine of theta needed to be negative. So the sine of theta here will be negative 4/5. Okay. So great. We have all the information that we need in order to write out all of the remaining trig functions, right? So we were given cosine of 3/5. Cool. Check. I'll just kind of box that up. And then otherwise, we have the sine of theta equaling negative 4/5. In fact, I'll rewrite that so it's just kind of cleaned up a little bit. And we'll box that up. Now let's get the tangent theta. It's going to be negative 4/5 over 3/5. Those 5s will cancel. Don't forget it's negative. And then you're going to give me negative 4/3, right? Let me check my notes. Negative 4/3. Looking good. Great. Let's do cosecant next. Cosecant theta, that is the reciprocal of the sine, so that'll be negative 5/4. That was quick. The secant is the reciprocal of the cosine. Where was the cosine? It was 3/5, so that'll be 5/3. And the cotangent will be the reciprocal of the tangent, so that'll be negative 3/4. Great. And then we're done with that. Okay. Very good. Done. So let me know if you have any questions on that. Again, this piece of information here, that theta was in quadrant 4, enabled us to determine that the sine of theta needed to be negative. And so that kind of drove this conclusion here, which allowed everything else to fall into place. Okay? Because remember, once you have the sine and the cosine values, you can piece together all of the rest of the information just using that, because everything else is based on sine or cosine or both. All right, let's do this one more time, but with different given information. Here, the cosecant of theta is 3, and the cotangent of theta is negative, less than 0. Okay, so if the cosecant of theta is 3, now that's one piece of information. We need that. And then, what can be said about any of the other 6 trig functions? Well, we could say that the sine of theta is the reciprocal of this, right? Which will be 1/3. Because that's the relationship between cosecant and sine. They are reciprocals of one another, right? So just flip it over and you'll get the sine. So that's all well and good. What can we glean from this piece of information? Well, this is saying, what's the cotangent? It is the cosine theta over sine theta. Cosine theta over sine theta. That has to be less than 0 or negative, right? But wait, okay, so the sine is clearly positive. It's 1/3. No negative sign in front of it there. So since the sine is positive, but the ratio between cosine and sine has to be negative, well, then that means that the cosine has to be negative. Must be true. Okay, so keep this in mind when we are trying to evaluate the, the rest of this biz. Okay, so now we can use one of the trig identities that was mentioned before, preferably one that involves the cosecant, because we have the value of that. I would go for this one right here, okay? And by this one, the start, okay, hold on. Let me underline it, this one right here. That's got a cosecant squared in there, and the other unknown there is the cotangent, which is exactly what we want to be solving for that, okay? And we know that it's negative, and we know also that the cosine has to be negative, but you know, that might actually not be super relevant here. Okay, so in any event, here is that identity being used, the cotangent squared of theta plus 1 equals the cosecant squared of theta, which is the same as squaring the cosecant. Okay, so everyone feel me on that? And therefore, the cotangent squared theta plus 1 has to equal 9. Let's go ahead and subtract 1 from both sides. That means the cotangent squared theta equals 8. Let's take the square root of both sides, and remember, you're going to take the plus or minus square root. We need both. And we'll know from this information that we're actually just going to take the negative square root. Yep, very cool to know that. So that means the cotangent theta has to equal the negative 2 root 2. Now that's me simplifying real quick the square root of 8, and that's just because I've been working with that number a long time. So if you have questions about that, we can go into that a little bit further as well. Okay? Cool, cool, cool. So let's go ahead and use this information in order to, okay, so that's the cotangent. Let's box that up. That is a final answer right there. But let's use this in order to sine, or excuse me, find the cosine value, because we have the sine, right? Okay, so we know that this is cosine theta over sine theta. So that's going to be cosine theta over 1/3 is going to be equal to the cotangent, which is -2√2, yeah? Okay, so in order to excuse me, sorry, in order to solve for cosine theta, we need to multiply both sides by 1/3. Here we go. There's me multiplying by 1/3 there, and multiplying by 1/3 here. Okay, so this 1/3 and that 1/3 cancel out. We're just left with cosine theta. Multiplying by 1/3 is kind of like you can extend that line there, and then the 3 just kind of slips into the denominator position, and we'll have -2√2 over 3 will be cosine theta. Okay, check my notes on that. Yep, that's good to go. Okay. And then from here we can get the secant, because that'll just be the reciprocal. So that'll be -1 over 2√2 over 3, or just, sorry, flip it over. I don't need to go 1 over. I don't know why I keep doing that. Just doing it in too many steps here. You don't need this many steps. I need to come to recognize that. I can show you the rationalizing the denominator step, though, to explain how I'm getting the final answer of -3√2 over 4. And that'll be, yep, my secant theta. And then, so let me go ahead and box that up. Okay, so what do we have? Cosecant, sine, cotangent, cosine, secant. We need the tangent. So tangent theta is sine over cosine. So that's 1/3 over -2√2 over 3, which is, I mean, go ahead and cancel out those 3's. And you'll have 1 over 2√2, still negative, don't forget that. And then rationalize that denominator. And then you'll have it the final answer, -√2 over 4. There we have it. Let me just make that a little bit more appropriate as far as the position is concerned. Okay, do we get them all? Tangent, secant, cosine, cotangent, sine, and cosecant. Yep, all set for that one. Cool. Moving right along. Remember, ages ago when we first talked about even and odd functions, and how even functions are reflections over the y-axis, graphically speaking, and that odd functions were rotationally symmetric over the origin. Well, the same is true here for the trig functions. Some of them are even and some of them are odd. So which ones are which? Well, the cosine and the secant functions are even, which means, of course, that you can fold them in half, the graphical representations over the y-axis, and those trajectories will like lay on top of one another, or said another way, they're mere reflections over the y-axis. Furthermore, algebraically, when you plug in negative inputs, the outputs are just the same as if the inputs were positive, is what I mean to say. And then for odd functions, the sine, cosecant, tangent and cotangent, those are the trigonometric functions that are odd, so they have a rotational symmetry about the origin, and furthermore, when you plug in a negative input, that negative sign kind of slips outside of the function. That's the way that I like to think about odd functions anyway. That's what's helpful for me, and if it's not helpful for you and you have another way of thinking about it, by all means, like, do it your way. So let's go ahead and use this information in order to simplify the following examples here using even odd properties, okay? And of course, we're not going to use a calculator, as is the instruction associated with these examples, so no problem. So notice that our first example involves the sine function. Now the sine function is odd, which is to say that it is equal to, when you have a negative input here of a negative 135 degrees, that is equal to negative sine of 135 degrees. And what is the sine of 135 degrees? Well, unless you have unit circle memorized, you can go ahead and reference, where's 135 degrees? There it is. And the sine of it, oh, it doesn't, oh no, it does matter. There is some SIGN differentiation here. Cosine's negative root 2 over 2, but the sine is a positive root 2 over 2. Okay. I'll hold the phone. Yep. And then it's negated after the fact. Okay. Yeah, I checked my notes and I'm like, oh wait, my answer is negative. And that's because of this negative sign out here. Okay, so just to be clear, if we're just talking about the sine of 135 degrees, it is positive root 2 over 2, but the negative sign coming out of the function by virtue of the function being odd makes it negative, okay? Cool, so hopefully that all lands and makes sense for everybody. All right, next one. The cosine of negative 270 degrees. Well, the cosine, if you'll recall, is an even function, which means that it is equal to the cosine of positive 270 degrees. Oh, you know what? There's a convention here that I did not uphold. I am so sorry. When you have negative degree measures, it's customary to put them inside of parentheses, but once they're positive, you should take them out of parentheses. Okay, so I'm going to try and be a little bit more consistent with the notation there. Okay, and what is the cosine of 270 degrees? Oh, and I did not mean to put a third line there. The triple bar equals sign means is equivalent to, which is a little bit different than straight up equality. Okay, so 270 degrees, where are we? There we are. Yes, right there. So that will be having what value? 0. Look at that, because the cosine value is 0, aka the x value at that position. Okay, so therefore it'll be 0. Okay, one more of this type. Let's go secant of negative pi. Secant, huh? Is secant odd or even? Well, the secant function, it looks like, is indeed, it is even. So that means that this will be equal to the secant of just pi. Okay? So the secant is 1 over the cosine, right? So the cosine of pi, again, we can look at unit circle if we want to. Where's pi? Here's pi, and the cosine is going to be negative 1 at pi. So that means this will be equal to 1 over negative 1, which is negative 1. Let's go ahead and box that up. Donezo. All right. Now, here is just a little bit of information that I wanted to make sure I just threw in to lecture. This is from your textbook, and it just goes through giving you options for how you can find the values of your remaining trigonometric functions when you have like a little bit of information. So it's like option 1 is using the circle of radius r method, which is a multi-step process here, and you have to at least take all those 4 steps, and maybe even more if some of the steps are a little bit more complex. Whereas option 2, you're just going to, you know, use identities to replace one for another, and you know, it's probably going to be a little bit more straightforward to use the identities method. Okay, so I just thought that that was pretty valuable to compare different methods here. Certainly not wrong to go option 1. It just might be a little bit more time consuming. Now that we know the properties, the properties and the identities, it'll probably behoove us to use them because they are acting quite a bit like shortcuts here and there. Okay, let's go ahead and wrap things up with just a few more examples. And by a few, I mean 4 more examples, in which case we are just going to be using the properties to find the exact value for each expression, and don't use a calculator. And I know what you're thinking, at least for these first 2 that you see on the screen. Uh-oh, I don't know anything about 18 degrees or 20 degrees in terms of even sine and cosine, let alone secant and tangent and cotangent and all that other business. So what am I going to do here? Don't sweat it. All of these problems are set up to be useful in using the properties. Things are going to cancel out in really super fun ways once you get into the hang of it, okay? So here's what you should do for this first one. Notice that you have a secant squared and a tangent squared. So it's your job to basically, I'm going to reference the properties box. So let me just go back a couple of pages and show you what I mean. So this fundamental properties box, this is the thing that you'll want to reference for this last set of examples, okay? So if you can turn to that page physically, or at least look at it while we're going, you're going to be looking for what you deem to be probably the most appropriate identity to substitute one value for another. So I'm looking at this and I'm saying, ooh, that secant squared of 18 degrees, I can replace it with a tangent squared 18 degrees plus 1, and I think that's going to be useful in in a subsequent step, because believe it or not, those tangent squared 18 degrees are going to cancel out. Watch this. It's a fun trick, okay? Here we go. So this is equal to, because I'm going to replace this one with a tangent squared 18 degrees plus 1, right? So this alone, the one thing that I've written here, I'm going to underline it in this hot pink and underline this, right? It's a direct replacement one for the other in regard to the identities. And then, of course, we're still subtracting off tangent squared of 18 degrees. But notice that this and this cancel out, don't they? Yep. So I'm going to do the canceling, I guess, in green for no particular reason. Boop, boop. And then we're just left with 1. Isn't that fun? So therefore, the final answer here is a 1. Cute. Okay, and the subsequent examples work similarly, but it's your job to look very carefully at what you're given and see what an appropriate substitution would be, okay? So here for number 82, this one's probably so easy it's hard. Notice that the quotient a term that we're given here is exactly the same as the cotangent, right? The cotangent of theta, or 20 degrees, and specifically in this case, is equal to the cosine over the sine of 20 degrees for each one of those. So essentially, this is equivalent to cosine 20 degrees minus cosine 20 degrees. You guys see that? Of course, I'm going to write the wrong thing first. Or sorry, cotangent. Oh, my bad. Yikes, cotangent, not cosine. Cotangent 20 degrees. Sorry, let me say that again. Cosine 20 degrees over sine 20 degrees is exactly the same as cotangent 20 degrees. So you have something minus itself. What does that always equal? A big fat 0. Okay, so for these problems in this in this set, they're going to be, waiting for you to find the trick, basically. So you need to be super duper clever in being able to find the tricks, and they get harder as you go. Okay, moving on to number 86, and we're almost done here, folks. We have, yep. secant of negative pi over 18 times cosine of 37 pi over 18. Ooh, 37 pi over 18, yikes. It looks like we need to think about this in terms of, well, I think we can use the periodic nature of cosine in order to find, let's see, we got a denominator of 18. It sure would be nice if we could double the 18 as far as the number of pi's that are happening in the numerator, because then we could take out a factor of 2 pi, which is, you know, equivalent to 0 radians, and then we could just see what's left over. So 37 pi over 18, that's the same as 36 pi over 18 plus pi over 18, right? And then this right here, let's go back to that hot pink. I like that color. This goes to 2 pi, which is equivalent to 0 radians, right? So it's really like we have cosine of pi over 18. You feel me on that? Furthermore, secant as the type of function that it is, whether it's odd or even, secant is an even one, right? So the fact that we have a negative pi over 18 inside of the secant, it's actually equivalent to secant of pi over 18. So we can do these two adjustments here and say, all right, that means that this has to be equal to secant pi over 18 times cosine pi over 18. And what's the secant defined as? Well, that's 1 over cosine pi over 18. And then that's multiplied by cosine pi over 18. Well, those cancel out, don't they? Because, you know, you can put this cosine pi over 18 over a 1 if you so desire, just to make sure you know who's in the numerator and who's in the denominator. You go boom, boom, and that's going to be equal to a 1. And there you have it. Done deal. Great. One more, and then I will let you go. How are we going to get through this? Ooh, check this out. Couple of things are happening with this cosine. Notice that it has a negative degree in its argument, and furthermore that degree measure is well above 360 degrees, so we have a full rotation that we can take out. And furthermore, since cosine is an even function, we can just kind of let that negative sign kind of dissolve away. Furthermore, the tangent right here, well, tangents are odd functions, so that negative sign can be pulled out in front of the tangent. So we'll keep that in mind as well. All right, so a couple of things to do. Let's go ahead and deal with this first. So that's like negative 360 degrees, and then what's left over? A negative 70 degrees, right? Okay, and good, because we got 70 degrees all the way around the rest of this problem anyway, so that would make sense. Okay, so this bit just kind of goes to 0 degrees, right? It's like a full backwards revolution, and then we just have this negative 70 degrees left over. Okay, so that means, at least initially here, we can say that this is sine of 70 degrees over cosine of negative 70 degrees. Plus tangent of negative 70 degrees. Okay, now let's use the evenness and oddness of these trigonometric functions to make the signage adjustment. And by signage, I mean S-I-G-N, sign adjustment, not S-I-N-E. Sine of 70 degrees over cosine 70 degrees. Yep, because cosine is even. And then that's added to a negative tangent 70 degrees. Sine over cosine, same theta, that's going to be tangent 70 degrees. See where I'm going with this? Plus a negative tangent 70 degrees. Oh, those are opposites. They will cancel each other out. Oops, I meant to do the pink there. Let's undo that last line if possible. Boop, boop, cancel, cancel. We're left with 0. Little anticlimactic there at the end. But that's what you're going to find is mostly the case with problems like this. When you have weird degree measurements, unless of course the instructions are like, you know, do some button pushing on your calculator and give me a decimal rounded to 3 decimal places. I'm not as much interested in that. I'd much rather see you guys use these properties correctly. And that's, yeah, what the crux of this last problem set is in this section. Okay, so let's have a fantastic discussion in class, and let me know what you think about this. Thank you so much for your attention, and I'll see you soon.